Okay, I think we should start. Hi, everyone. We are continuing with the ACRC webinar series, and this time I'm very happy to have again Professor Bernhard Wicht from Leibniz University in Hannover. This time he will talk about DC to DC converters. So we are very happy to have you again. Please start.
Yeah, hello everyone. Hope you can hear me well. Thanks for the invitation and for the kind introduction. I'm happy to again talk about, wait a second, I switched to my pointer. Yeah, so I'm happy to talk about one of my favorite topics out of the area of power management, which is entitled Analog Building Blocks of DC-DC Converters. So it's really my honor and pleasure to give this talk. This talk is co-organized by the IEEE Solid State Circuit Society, as well as by the Advanced Circuits Research Center at the Technion. And in particular, I really have to thank Masha Schuster for organizing it, and as well as Professor Kwatinsky. And with this introduction, I think we're ready to start. So let's first take a look. What am I going to talk about in this roughly 1 hour? That's what I'm planning. So after a short introduction on DC-DC converters, we will look into the key element, the power stage, consisting of power transistors, gate drivers, level shifters, and so on. As well as then later on, we go into, I would say, a more classical analog design topic, which is related to the control loop. And that also includes techniques like current sensing. And finally, we put all together and take a look at things that need to be considered on system level. So let's first look into the introduction. How does these DC-DC converters look like? There may be some participants, I'm sure, that have seen my presentation a couple of weeks ago. So you may remember this chart here, or this picture, which basically illustrates what DC-DC conversion is about. DC-DC converters are the key element in the growing area of power management, and they simply link the voltages that occur at the application level from various energy sources with various voltage levels to IC level voltages that we see here on the right. And important characteristics are the output voltage for all these different electronics here on the right. At the right power level means load currents that can even vary over the operation. And in the end, we want to efficiently use our energy sources with a maximum of power efficiency. So this is the general idea. So if you look now into this DC-DC converter block, there are various ways to implement these concepts. The fundamental characteristics is switch mode operation. So we can now use switches plus some discrete components, some passive components. That can be capacitors. Then we have so-called switch capacitor converters. It can be hybrid converters that combine both L and C components. But the classical DC-DC converter stage is the one that I'm showing here, which is the inductive conversion. In fact, we have a DC-DC buck converter that we show here. It uses switches, which are controlled complementary. That means if S1 is on, S2 is off, and so on, and vice versa. So by doing so, we basically convert our input voltage in a pulsing switching node waveform, as shown here on the right. And now it is followed by a LC low-pass filter, which basically builds the average voltage out of these pulses, which leads to the output voltage as shown here, which is more or less a DC voltage. Of course, there's some remaining ripple, but more or less it's a DC voltage, which is the average of the pulsing behavior here, pulsing waveform. So that leads to the way to control it. So the pulse width if you control the pulse widths properly, then we can set also the level of the output voltage accordingly. So switch mode operation and pulse width modulation are the key concepts that we find in a lot of, or in a majority of power management DC-DC converter circuits. So now this is the so-called power stage, and now we want to add a control loop around to keep a stable output voltage under all conditions. And that's shown here on this slide. So the upper part again shows the power stage here, and now on the left we add a pulse width modulator that allows now to control the on time of these two switches. And now the feedback loop is closed, or the loop is closed by the feedback here, by the actual controller, which consists of a resistive divider that builds or generates a measure of the output voltage, a downscaled version. And then now we feed that to an error amplifier, which compares it to a reference voltage and gives out the deviation between the set value and the actual value at the output. And this whole circuit needs to have a certain frequency behavior, which is set by this Z0 block here. In the end, that's why this whole thing is also called compensator. So we will talk about this in a few minutes. So we close the loop. And now how does the pulse width modulation work? We can see that here on the right-hand side. If at each cycle of the switching operation, the PWM signal turns on the high side switch, which is this one here at the upper switch. So this way we bring energy into the system. At the same time, our sawtooth generator, as part of the pulse width modulation here, starts to generate a ramp. And as soon as this ramp crosses the error amplifier output voltage, we switch from we turn off the high side switch and turn on the lower switch, so that we build a freewheeling loop here consisting of the LC and that switch. And by doing so, we can control the amount of energy that goes into the system. And by adjusting now the duration here, we can implement a stable control for the output voltage. I'm also indicating the case that we have a load step here at the output, which pulls down the output voltage. This way, due to the inverting behavior of the comparator, our VC voltage will go up. This is the dashed line here. And we see immediately our crossover point with the ramp occurs at a later time. So we expand our on time, which results simply, or which allows us to counteract the increase in current, so that that we deliver more energy to support the higher output current. So this way the control happens. And at the same time, this block diagram already indicates several blocks that we will address during this lecture. Some blocks in a little bit more detail, some just briefly. Includes power stage and the feedback loop blocks, as well as techniques like current sensing, monitoring, and protection. The whole implementation on IC level is closely related to the technology options. So, which I'm summarizing a little bit on this slide. So again, we have our loop with all these different colors. And of course, in order to implement a power stage, we need to have transistors which can withstand higher voltages. That starts with 5 volts, but can be up to 100 volts in typical technologies. And at the same time, they offer low on resistance values, so that we can handle currents in the few amps range across the chip. So then the control loop components, they are more classical low voltage analog transistors. So we find a variety of analog as well as digital transistors with various ratings, as well as even bipolar transistors in some technologies. On top of that, we may need some isolation, which is in the easiest case some buried layer isolation for floating or for different switching nodes. We also may need, we may find trench isolation. This is a topic we also talk about in a few minutes. And finally, some other components like various diodes, as well as memory, even non-volatile memory, flash memory is available. So just to briefly see how technology supports the DC-DC converter design. With that, we can already go into the power stage. So the power stage in DC-DC converters can be found basically in 4 configurations, as we see here. So it's in the simplest way to implement it, it can be a low side switch. So the switch is located at the lower side and connects the load from the battery to ground. The opposite way is called the high side switch, right? The switch here at the high side. And if we combine both together, we form a half bridge. And again, a half bridge, two half bridges form a full bridge. And sometimes also referred to as H bridge, right? Since this is like the character H. For higher power, the transistors will be discrete components that are placed off chip. But if the power is in the range, we talked about currents, right? If we need to deliver currents in the few amps range, we can still handle that as an integrated power stage. So of course, if we have high currents, we really need to aim for low on resistance values, which unfortunately comes along with the higher W, high width of transistors. So they get really large, and with that we get large gate capacitance. So especially for fast switching DC-DC converters, we get losses, and so it's always good to find a good optimum between too many losses and too high on resistance. And this is also the reason why we use N-type transistors, especially for high power and high voltage applications, as they give us a lower RDS-on value, usually, and lower area, lower gate capacitance. Of course, if you use N-type transistors, I'm using them here already in these 4 configurations. If we have a high side implementation, our load will be switched to battery level if you turn it on. And in order to keep the transistor turned on, our gate voltage needs to be higher than battery. This is something we also need to talk about. So how to provide the gate supply properly. So talking about the power switch, let's look at some parasitic effects which occur if we have inductive switching, which is the case in DC-DC converter designs. So the first one is that we may get a parasitic bipolar behavior. Let's assume we have such a transistor, and in fact, it can be any transistor. It doesn't need to be a DMOS transistor, high voltage transistor. It can be a regular transistor, maybe 5 volt, 3 volt ratings. Then if there is at the drain, if you have an inductive, or if you have an inductor connected, right? We have seen there is an inductor in DC-DC converters, then it may pull this pin below ground, which causes the drain junction here to turn on, the N to substrate junction to turn on, which at the same time is this kind of so-called body diode that we see here. But it's not just the body diode, it's at the same time the base emitter junction of a parasitic NPN bipolar transistor as indicated here. So as soon as this goes below the forward voltage, below ground, which means roughly 0.7 volts minus, we get the base emitter junction conducting, and the collector is formed by any nearby N area. So any N val nearby, that could be even a sensitive analog circuit, acts as the collector. So it's obvious there will be some disturbance of other blocks. We may get some substrate debiasing, and in the really worst case, even latch up. So that's quite risky and needs to be avoided. So the rule of thumb is that we set all the pins that go to all the connections that go to pins at the package of our IC should be surrounded by a guard ring. So it's quite simple. We see that here at the bottom. So I'm not so much in favor of using animations, but I thought I do this in 2 steps because otherwise it's too much color and too many structures. So let's quickly go, or let's slowly go into this guard ring setup here. So we simply, first of all, of course, spacing already helps. So that this bipolar will be already degraded if we place the other N area in distance. But it's even more efficient to place a guard ring in between. So this guard ring acts now as a collector and supplies the collector current. This way, there's almost no current that goes to the other blocks and disturbs the blocks. So that's the key idea of placing guard rings. Of course, there is still a bipolar effect that's still there, but we don't see the disturbance at the other blocks. That's the key idea. Of course, if sometimes it's not so efficient, maybe there is some really sensitivity there, then we can place even a double guard ring or triple guard ring, which of course expands here the area, extends the area. And this is a general drawback of placing guard rings. It costs area. And this way also there is silicon area required, and that's relating to cost, of course. So, but in the end, it's required to support this inductive switching. And if we are still afraid that there might be some disturbance at any other block around, we can encapsulate those circuits. So assume this little transistor here is our sensitive analog transistor, then we can place this kind of encapsulation around to further suppress any coupling. So that can be a highly doped area again. And then we have our buried layer isolation, which I mentioned briefly in the technology options a couple of slides ago. So that's basically on parasitic effects, which are based on bipolar transistors. There's one more effect I briefly wanted to address. So this is called substrate coupling. You can imagine for this pulse width modulation, these pulsing waveforms, they have quite steep slopes. So we easily achieve 10 volts per nanosecond. And now assume that we use some kind of isolation also around the power stage. So this looks similar to what we have seen, but this is now a power stage, which shows exactly the switching waveform. In the end, that's already linking to what we will talk about in a few minutes, but it's probably quite straightforward to see that there is a switching node activity. And we have with that, we have this whole isolation well, which is required to move up and down at very steep slopes. And this reverse biased junction here is also representing a relatively large capacitance. And so we get displacement currents in the substrate. And we all know that our P substrate is, of course, not a zero ohms connection. It is also has a finite resistance. And now this displacement current flows across this distributed resistance towards ground, system ground. And so we get some voltage drop. We get local substrate debiasing, and that's really huge. So we can easily assess or estimate the current peaks that we see in the substrate, which reaches in the order of 100 milliamps. And that's why we get local substrate debiasing in the few volts range. And that doesn't only cause malfunction of analog circuits, it even may cause some bit flips in the digital logic. So that's really scary. And I've seen that in our own lab experiments a couple of years ago, before we learned how to do it, that may happen. So we need to do something about it. And that means we can do backside metallization, for instance, to place a conductive surface here at the bottom of the wafer, or bottom of the die. Then we immediately at the root cores, we suck away the displacement currents. We could also place a conducting trench isolation left and right of these sensitive devices or of these noisy devices. That would help, but it's not always available. And then in the end, we can place other guard ring structures, which are sometimes efficient, sometimes not. So there is a lot of tricks, but anyway, I would like to make that also make a point here. Substrate coupling is the second parasitic effect that is important and to be considered during design. Okay, now we have our power transistor implemented. Then we need to drive it. That leads us to the gate driver circuit block, which is a very simple function, right? Gate drivers are intended to turn on and off our power switch, which can be a low side, as shown here, or a high side device.
I'm sorry, can
Yes.
I ask a question, or you want questions after the lecture?
It's fine if you have directly, yeah, why not?
Yeah.
Is it on this slide?
No, on the previous one, and
All right.
actually
Yes,
both
sure.
on parasitics and mostly on substrate coupling, I actually have two questions. One is if you have any estimation for the distance between switching regulator and other circuitry where substrate coupling effect kind of decreased to, let's say, acceptable, reasonable value. This is first one. And the second one, if we use SOI or pseudo SOI technology, it will solve most of the issues that you spoke in this slide and previous one, but would it bring any new effects that we are not aware of?
Oh, very good question. Thanks. So I try to keep it compact. We may get back to it even after the presentation. First of all, how much coupling we get can be estimated. In the end, I would say it doesn't help. We need to do some TCAD simulations in the technology to really know what's going on. That's also something that we started. In fact, this is a link to a paper that we published. It's been quite a while ago, but there is a nice table that shows some of the effects and some of the structures that we can implement to reduce the coupling effect. Also in terms of percentage, very simple. And this was verified by measurements, at least partially. So that's the nice thing about this paper.
Yeah.
So, and the other part of your question is SOI. So in fact, we also use SOI in some of the projects recently. And that's fantastic because I forgot to mention, and it's good that you bring it up in the slide before here, this bipolar effect goes completely away. Since we have every device locally, basically in such a buried oxide, locally isolated, it's more or less like we identify here. So we can encapsulate all the power stages. So bipolar effects are gone. However, we still have capacitive coupling effects. And that's something that I feel there is no real methodology in SOI yet, how to do a proper design to keep your capacitive coupling under control. That doesn't matter if you have high power applications, because then your coupling current is negligible, hopefully. However, if you want to have your DC converter also operating at low power, right, with quite some efficiency, then we realized in our projects that the amount of capacitive coupling currents may really impact efficiency, since there are some losses, of course, associated with it. And especially if you do a high voltage design, and I assume if you talk about SOI, SOI is of course really, really great for high voltages, up to a couple of 100 volts. And then of course these slopes will be simply steeper. And so we get some coupling. So SOI is great, except that we need to take care of the coupling effects, right?
Okay, thank you very much.
Sure, you're welcome.
Can I ask another question?
Oh yeah, sure. Then I'm fully okay with that.
How about using EPI with the high concentration, the substrate?
Yes, that's also a good point. So at this point, I always need to say I'm not a technology person, but of course I know what you're referring to. We studied this this paper here actually looks at various EPI concentrations, and that's really, really sensitive to. It really depends the coupling effect. Really depend on the EPI concentration. So you're fully right. There may be a lot of different effects depending on your material.
And another question: in case of SOI, there is an isolation silicon O2 between the NMOS and the substrate, which also isolates the thermal conduction. Is there any significant effect of overheating of the N channel?
Yeah, that's this self-heating. Self-heating and SOI, of course, that is a topic which in pure silicon it's much better. You get much better your heat out. That's why my personal experience is that we focus on reasonable power levels in fully integrated or highly integrated DC-DC converters. In SOI, I personally do not have the experience with, I would say, high power SOI designs. I simply can't comment. I know that's a topic that's been there's also ongoing research on that for, I don't know, more than 20 years already. But we didn't use high power. That means we restrict ourselves to currents in the range of a few hundred milliamps for fully integrated DC-DC converters in SOI. And we didn't have any issue with that yet, with self-heating.
Okay.
Yeah. All right. Thanks.
Yeah, I'm sorry. Yeah.
Okay.
Okay, I'm sorry. May I have one stupid question? So, in your experience, the soil technology and the bury technology, which one is better?
I'm actually right now, if it's high voltage, I'm really excited about SOI. It's a simple answer. If you look at these parasitic bipolar effects, they're really nasty. In my career, I had to deal with so many bipolar effects and to get them solved, right? That I'm so happy that we have SOI nowadays, which simply where everything disappears. So that's the reason. I would always go for SOI. And in fact, there's a lot of reasons that it may even pay off cost-wise because of that you have your bipolar parasitics better under control, and also in terms of silicon area, since you can squeeze down some power stages and so on. So it's actually looks quite good. Yeah. So is that my simple answer? Is that okay for you or?
Yeah, I'm okay. Yes, thanks.
All right, sure. You're welcome. So yeah, now we are really still at the power stage. Let's see if we yes. Now we go into the gate driver. So which of course combines the power transistor with the driving circuits. And that's actually in detail. If you look in detail, it's a little bit more than just turning on and off the switch. We see a low side driver, a high side driver here. And the drive levels, we will talk about that, are of course a little bit higher. Usually typical voltages that you apply at the gate source of your power transistor are in the range of 5 volts. For discrete devices, even higher, 10 volts. And so if we control it with logic that runs maybe from 1.8 volts or so, we need to have level shifters for the low side as well as for the high side. Then we need to supply our gate level, our gate drive voltage. Usually or typically it can come from a linear regulator. It can, for the high side in particular, we need to talk about bootstrapping. So that's the gate supply block. And finally, if we use a half bridge, which means we connect both transistors here, then we want to make sure that they do not conduct at the same time. So we need to have some kind of dead time control. So let's take a look at what's going on more in detail. So the gate driver itself, it's the definition of a gate driver. So that's a little bit busy, this slide, but it's my aim was to put everything on one slide that you need to know about gate drivers. So it's so it needs to turn on and off our power transistor. So basically, this is the equivalent circuit. We hook up the gate to a drive voltage to turn it on so that the transistor reaches its defined on resistance. For turning it off, we connect the gate to source. So very simple. But then we also want to turn on our device quickly. That means there is a second characteristics. It needs to have an appropriate driving capability, which means current over time. The gate, of course, is a capacitive load, and so we will see just the current peak that goes to 0 once the transistor is turned on or off. So in the end, the equivalent circuit looks a little bit more complex. we already talked about the drive level, which is typically 5 volts. So that's applied at the driver. Then, of course, our driver switches are not 0. So they have a finite value, which is in the range of 1 ohm. So still quite low, but also still not negligible. And that correlates to a sink source peak current that we apply to the gate, or we take away to discharge the transistor, the gate capacitance, which is roughly 1 amp. So that's a lot already. That's just the gate driver. And that's why it's worth to talk about this later on a little bit more in detail. I don't want to spend too much data today about parasitics, which are related to a longer gate line. If this is a discrete transistor, there might be a distance which accounts to an inductance, parasitic inductance, and that also degrades our performance. So there's, of course, we need to watch out for these effects. Let's take a look at a real low side gate driver. That could be really a design that's that would be already product level. We could find that really in some actual product designs. So very simple. We have the power switch on this side with all parasitic capacitances, which can be here combined all to a gate capacitance. And now the gate driver in the easiest case can be a CMOS inverter. And if the load is low, we use one CMOS inverter. If the power transistor is larger, then it's good to have a cascaded approach with multiple stages, which increase in driver strengths by a factor of alpha. So that's something we talk about in a second. And now on the left-hand side, we see a level shifter, which is controlled from a low voltage digital control, for instance. It's a cross-coupled level shifter, which is fully CMOS compatible. And it has 2 complementary outputs. Let's assume we turn the in signal here to 1. That turns on this guy here and pulls down our out N signal, which goes directly to the gate driver. So by pulling it down, the P device here turns on and pulls up V out P. So we have these 2 complementary outputs well defined. So now this one signal goes into, the 0 signal goes into the gate driver. We have an odd number of stages. So then we get a high signal here at the output, which turns on our device, our power switch. So now the question is, why do we need a cascaded approach here for the gate driver? We can first take a look at an example and then dive a little bit deeper in this cascaded approach. So I thought it's always good to see some real world example. This is, of course, not the latest and greatest, but that's something I did still during my industry time. We have this is a buck, an inductive buck controller IC. It's actually a dual buck, which means we have 2 step-down controllers on the same die. This is the circuit. So it's a controller because the power stage is off-chip. So the half bridge here, plus the L and C, as we have seen in the very beginning. So and now our drivers consist of such a cascaded chain of inverters. And as the transistors are off-chip and can be quite large, in this case, they represent a gate capacitance of 10 nanofarads. We want to turn on quickly, 15 nanoseconds delay from activating to turning it on. It should be very fast. We need to have a strong driver. So in the end, we reach a driver resistance of 3 ohms and a peak current of 1.5 amps with this design. And if we look at the final last driver stage, the W/L ratio of the N-type device here is really large. This accounts to 3.2 centimeters, 1.5 inches. So it's really something is visible, right? It's really impressive. That's why I'm highlighting it here. Of course, it's not implemented such as a straight line. It's an array of transistors, but still it's only the driver. And that's the reason why it covers quite a large area as indicated here. So each high side and low side driver accounts to roughly 1 square millimeter in size. So it's a square millimeter, it's really large. And so it's probably worth to talk about the right optimization in terms of these stages and scaling factors. So of course, there's not too much time to go into all details, but depending on the design goals, on the application needs, we now need to optimize for various goals. And from this optimization, we can conclude the number of stages and the value of alpha, which is the scaling factor. So the W/L ratio increases from stage to stage. And in general, often we find that the goal is to achieve a minimum delay. So we give a signal here at the left and we want to turn on with the maximum speed, which also lets you achieve a very steep slope in our switching transition. So the PWM transition will be very steep, and that reduces our switching losses. So it's a very relevant case. And that's, of course, it's known already for many years. So in the 1970s, from that time, we know if you want to drive off-chip capacitive loads, then it's good to have this kind of cascaded drivers approach with a scaling factor alpha, sometimes also called tapering factor, which should be in the easy estimation should be equal to Euler's number, which is 2.7 something, right? So in reality, we use alpha in a range of 3 to 6. And from that, we can calculate the number of stages. And also want to highlight this sometimes the question, couldn't we scale alpha and keep it different from stage to stage? However, if you want to achieve a minimum delay, a fixed alpha gives minimum delay. So we keep alpha constant from stage to stage. There are other applications that are not shooting for minimum delay, but they would rather get minimum power consumption in the driver. And this is also a little bit correlated with the die area. So if you want to have minimum power and minimum die area, then these are the constraints. If you have too many stages, we have a lot of inverters, and each inverter has cross currents. So that's, of course, the limitation. Too many stages is not the way to go, but too few stages is also not good, because then our driving strength suffers and we get some weak transitions with really slow slopes at the power stage. So that causes cross currents. No, that not only cross current, that also causes switching losses, excessive switching losses in the power stage, in the transistor. So, and there's somewhere in between here is the optimum value of stages and scaling factors. And the rule of thumb is that we use fewer stages compared to the minimum delay approach. And that means we need to have larger scaling factors. So few stages, larger scaling factors, even greater than 10, they lead to minimum power. There are a lot of papers on that. One which I personally like a lot is this one here. And in the end of this presentation, which is available to you afterwards, you can even find the list of literature and references. Doesn't matter if we go for minimum delay or minimum power, whatever we have, we need to ensure always that we are immune against the VDT, steep VDT transitions at the switching node, which relates to the Miller capacitor that we have at each power stage. And so this capacitive discharge current, so the Miller is a drain gate capacitance, it will couple into the gate driver. So our current needs to be supported by the gate driver. And if not, then we need to decrease the driver resistance simply by increasing the W/L of the last driver stage. And that's why this driver, the last driver stage usually is really large. So as we know that we have a large driver stage, the cross currents in the final driver stage, they may account to 50% of the driver losses. So it's maybe worth to spend some effort on that. So that brings us here to the optimization for power efficiency in the last stage. And what we can do here is, if you want to avoid cross currents in the last stage here, we first want to turn off one device before we turn on the other one. And that's one method to do that is to use a split path gate driver. As indicated here, we basically split our driver chain into two branches, one for the P device and one for the N device. This is our last driver stage. It's not the power transistor already. It's the last driver stage. This one here, this guy, this inverter. And now from the optimum design for minimum speed or minimum power, we simply change our driving strengths as indicated here. So the red guys, they get a little bit reduced W, and the other ones get enhanced roughly by 20 to 30%. I'm calling this asymmetry factor. So we make the whole thing asymmetric. And what we get from it is that the turn off activity always happens before we turn on the other transistor. And it doesn't matter which polarity, it works always. So you can simply follow the turn off on and turn off path. So it's alternating here to keep the signal properly aligned. So that's a nice implementation, because it also tracks process variations quite well. And above all, it doesn't have an area penalty. So all we do is we simply split our existing inverters here into two parts. Of course, there is some wiring overhead and there is some spacings in the layout, but transistor-wise, transistor size doesn't change. That's the main thing. So if you are interested, there is more to find in some of these papers here. So now we talked about the low side driver and in general the driver. This slide shows the high side driver, which is a little bit more challenging if we use a N-type device. The key blocks are similar compared to the low side. So power stage, gate driver consisting of scaled inverters. And the level shifter in this case is very simple. It's an example of a resistor-based level shifter. If you turn on the device here at the bottom, then we get a voltage drop across the pull-up resistor, and our gate drive signal will be generated. The nice thing is, if we hook now, and this is interesting, if we hook now our whole gate driver with its ground to the switching node, then we can use low voltage devices for the gate driver, as there is the voltage drop across is exactly the gate source voltage that we apply to our high side device. So typically 5 volts, that would be very suitable. Of course, some people may say 5 volts is already high voltage, but in terms of power switching, it's still a very reasonable low voltage, right? So they can be small devices that helps. And of course, the pull-up resistance shouldn't be too large, shouldn't be too small to avoid DC currents, static currents here. So 100K ohms is a good, a good trade-off. Then we also need to protect our input level here at the gate driver by using clamping diodes in either way, either this one or this one. That works quite well. And finally, we see here at the right a way to supply DC-DC converter power stages by a concept that's called bootstrapping. So we use a capacitor which we charge, and then so we charge it from a VDD supply, which may be a linear regulator that's available already at a 5 volts level. And as soon as the switching node is at 0 level, we recharge the capacitance C boot via a bootstrap diode, which gets some forward voltage. So we charge the capacitor, and if we now turn on the high side device, our capacitor will move up the bottom here. The button potential will move towards Vin. The diode goes in reverse conduction, so you can ignore it. And our capacitor is the only energy source for the high side driver, for the gate driver, and all other electronics that's connected there. So in the end, it needs to deliver the gate charge of the high side device plus any other DC current like in the level shifter. And from that, we can calculate the sizing basically by the gate, by the charge balance at this node. We can calculate the capacitance value. And typically we reach values of 100 nanofarads, which also indicates that we cannot integrate those on chip. They need to be placed externally. So in most DC-DC converter ICs, we have a dedicated pin, which is called boot or BST for bootstrap and so on. So with that, we can go to the control loop. So we have seen already the in the very beginning, the whole control loop block diagram. We have seen how we generate the PWM signal by this ramp.
Excuse me?
Sure.
Still, this is Michael from Intel. A question regarding power stage. You did not address parasitics on the power path, and actually frequently we have significant inductances at either on VSS or on VCC in nodes, and then actually every switching causes very, very significant LDI DT noise, and through Miller goes to the driver, etc. So do you have anything that you do to cover it, or you're just trying to minimize it layout wise?
Yeah, thanks for bringing this up. So of course I had to, of course I could talk for 5 hours. I didn't want to do that. So that's why I really had to take out some details. That's a good point. What I intended here is to focus on integrated power stages. And in fact, integrated power stages make our life a little bit easier in terms of parasitics. So the inductances in the power path that you're referring to would be here in the power path, right? We have inductance here at all the connections, drain, source, and also at the low side and towards the load. So, that's if we have a external power stage, this really matters. And we get some local LC tanks which are parasitic and which cause some ringing, and that's what you're mentioning. So if we implement the power stage on chip, it's a little bit easier. That's something I feel we spend a lot of effort on that. If you keep short connections and also the bond wires very short, or even flip chip, chip scale packaging, these things, that helps. However, if you have discrete transistors, then that you get easily a few nanohenries of inductance, and then you get ringing. So there is a lot of effort in the layout, also in the mounting, and how to build your PCB, right? All these things that you're mentioning. There's no magic. We need to keep this very short and small loops. Plus, some techniques on circuit side is blanking. Like in the very first moment, you blank your sensing circuits so that they do not get disturbed by the ringing. That's the quick answer I can give in this moment.
Can it lead to stability issues? I mean, the L parasitics coupled with C-gate, this LC tank, can it introduce a pole or a zero that can lead to stability issues?
Yes, actually, it's two things. It's stability issues, and it's also that we get over this ringing that we get can also exceed the maximum ratings of the power stage. So one thing is that usually these transistors are rated much higher than the V-in level. In discrete, I think if you do a discrete power stage, there is a factor of 3 at least to really leave headroom for ringing, so that the transistor doesn't get destroyed. And the other point is the instability that you're mentioning. Yes, that is can quite easily happen, that your sensing circuits, right? This is of course only the power stage, but your control loop components, they may get triggered. And that's why a very simple approach is, in the very first moment when you have your switching, you simply blank and mask your sensing circuits so that they wait until the ringing decays, and then we do the sensing.
Okay, I see. Thank you.
Okay. Yeah, thanks for this making this point. So the control loop. Now we have seen the PWM generation, the control loop, and now there is this concept that we see on the right hand side. This is called voltage mode control, and it works nicely. It's very common. However, if you do the calculation of the transfer function, which I left out in this presentation, otherwise would be probably a little bit boring as well, but can be done. Also, it's also relatively straightforward. Then we indicate or we identify that we have this LC here at the output causes a double pole, and this makes it relatively slow to react. And in addition, the loop stabilization is quite complex. That's why it's recently, over the last couple of years, there is more and more attention paid to current mode control. It has a similar approach. However, the main idea is to replace this ramp here, which comes in the voltage mode control case from a sawtooth generator, to replace that by the inductor current, which already is a ramp, and it's of course a current signal. And if you convert that into voltage domain, we can run this similar scheme here and turn the PWM signal, switch it if you have a crossover. If we then do the transfer function calculation, we identify that we have a first order system, and that's great because now it's much easier to stabilize. It's also faster in reaction, and it's just the disadvantage is it makes it much more complex. So the whole block diagram looks even more complex since we need to measure the inductor current. So also for with respect to time, I left all these details out and would like to just highlight how to compensate the voltage mode control. Frequency compensation is achieved. Maybe I go quickly back 1 second. The compensator here, this is the guy that needs to take care of our frequency compensation to achieve a stable phase margin. So this Z0 block is usually an C and R configuration. There are various types available, and I'm showing here the type 2 compensation in this slide. So we insert zeros and poles, and if we size and position everything properly, we achieve good phase margin, which is usually 60 degrees, a little bit more maybe. And this kind of compensation, if you do the calculation here, it's, of course, we have an inverting behavior. Here, this is the minus. Then we have a voltage divider, feedback divider here. Then we have a pole, which is the integrator pole coming from the GM and C1 pole at DC, plus a regular zero and a pole. So the feedback transfer function would be as shown here. And now usually the loop gain or the poles are and zeros are sized such that our loop gain, which is this one here, H, and the control to output part, which is not shown here. So it was, I used the term G for that. So G times H has a crossover frequency which reaches 0 dB in between the zero and the pole here. So that's usually the target. And with that goal, we can size our C and R components. And sometimes we achieve really large values, unfortunately, so that we cannot fully integrate this compensation here. So we need an extra pin, which is good because then you are flexible to size your own frequency behavior. However, some customers, some applications do not want to bother with these stability issues. So they would like to have everything fully integrated. And then these products and these designs use integrated C1, C2 values by means of a so-called cap multiplier, capacitance multiplier. So basically it uses something like a Miller effect to virtually increase the cap value so that we can still integrate it on chip. If you're interested, there's a nice paper here as well, which shows these techniques. Let's look at some circuit blocks since we entitled this talk Analog Building Blocks. So of course, let's get back to circuits and building blocks. The key element is the error amplifier. It's responsible for load line regulation, transient response, and so on. And as in many control loop designs, we don't want to have the loop gain too large. And that's why we use reasonable medium gain stages like a symmetrical amplifier, or sometimes even cascode op-amps can be found. So this kind of textbook circuit, which I'm showing here. However, we noticed just before in the transfer function for the controller, the GM of that stage is part of the transfer function. So we need to have a good control of the GM, which is indicated here in this diagram. In such a simple stage, it would be just the transconductance of the differential input pair, and this can be sized by or set in design by the beta of these two transistors, WL and so on, but also by the bias current of this differential amp. So just to briefly mention that. Now imagine we start our DC-DC converter and our output capacitor is fully discharged. Then our error amplifier will see a maximum delta, and it will attempt to dump as much current into the output as possible. And that leads to inrush currents. And that's why, and it's usually not really desired to have these inrush currents. And so that's why we still, a lot of designs use a function which is called soft start. So to prevent inrush currents. In the end, we want to make sure that our output voltage at the output of the DC-DC converter has a soft slope, very weak, in the range of 1 to 10 volts per milliseconds. So we slowly charge up our output capacitor before the whole thing is stable and runs. And that's why we use, we can expand our error amplifier that we just have seen at the slide before by this little soft start function, which basically bypasses our reference differential transistor here with another transistor. And so if we start our DC-DC converter, we give the enable signal to 1 that turns off this transistor. So we start a ramp, which starts basically from 0 by charging up this soft start capacitor. And this transistor basically takes over and bypasses the main transistor here. And so we slowly ramp up until it reaches the maximum level here. Then this transistor, again, that's automatically turns off, and we get an automatic transition to the main differential transistor back again. So if you want to achieve, for instance, 2 volts per milliseconds, and we allow ourselves a capacitance of 5 picofarads, we can calculate a very low current. So it needs 10 nanoamps here. And that's why I'm showing here this little current mirror. If we have a reference current, bias current of 1 microamp available, usually we have that on chip level, then we can use this odd current mirror, which reaches 100 to 1 of current scaling to achieve this 10 nanoamps. And I like this circuit. I also like to show it to my students because it violates all the matching rules we have learned. It's 10 to 1 and 1 to 10. So that usually we wouldn't do, but it's compact and it has some spread, of course, but it doesn't matter because we just want to be in that range of 1 to 10 volts per millisecond to avoid inrush currents. It doesn't need to be very precise. So one more block, it's the sawtooth generator. So that's the block that generates our ramp. However, we know at the beginning of each switching cycle, we cannot immediately reset this ramp from max to minimum value. We have some finite settling, and it obviously eats up some part of our duty cycle resolution. So that's something we need to be aware of, especially for fast switching DC-DC converters. The second point I wanted to mention is, of course, the ramp generation is straightforward. We have a capacitor and we charge it by a current source. However, this ramp would start really at 0 level. And that wouldn't fit the common mode output and input level of the error amplifier as well as of the comparator. So you may remember in the control loop, we have the, especially, let's say the comparator. The comparator wouldn't fit to 0 level. Could be, but usually it's better to use a active integrator circuit, which allows us to set the start point of the ramp by the reference voltage. The reference voltage is at the same time buffered since it goes to the non-inverting input of this op amp here. So that works quite nicely. So that's an easy circuit to be implemented. If you have a fast switching, we still may even implement 2 of these circuits and operate them in a time interleaved manner so that we get a nice triangular sawtooth ramp as shown here. So we have verified that up to 50 megahertz, it really works nicely if we do that this way. So that brings me to probably one of the last interesting topics. So yeah, that's fine. So watch a little bit of time. But anyway, current sensing is used at various locations in DC-DC converters, power management. It can be open loop, for instance, to protect the main power stage, to keep it the transistor within its safe operating area. So of course, we know that if our drain source voltage is still large, then we don't want to have large current at the same time. So we need to watch that. At this, the second point is we can use current sensing in closed loop operation, for instance, in the current mode control in DC-DC converters, as we just talked about briefly. So what's the easiest, straightforward way to do current sensing? We use our power stage itself and measure the voltage drop across. That works, but of course there is a lot of variation, so the accuracy is not that good because our on resistance may change over process variations and temperature and so on. So the other concept is much more common in power management design. It's so-called replica sensing. What we do is we use our power stage and we use a little fraction of that transistor as a sense transistor. So the scaling is here M to 1, while M is typically 1,000 to 10,000 as a scaling factor. So the sense transistor is really small. It's usually placed in as part of the power transistor array. And now there is a control loop which equalizes or aims to equalize the voltages at both sides here. And if we achieve that, we can do the calculation that our current that flows here at the output is 1 over M of the input current. This output resistance converts it to a voltage which is ground referred and is a measure of our input current. So that's the concept. It works nicely. It's just a little bit more complex. And as this is a control loop, we can even put together the block diagram of the whole thing. And now you see why I'm using colors. So we can link everything here. So, and from that block diagram, it's also a few steps to achieve the transfer function, which links the output current to the input current. So output current is here, input is here. And that already identifies, we have a 1 to M scaling. That's really great. And it also allows us, if we do the precise calculation, to identify our loop gain. That's the one here in the denominator. And from that, we can estimate the gain bandwidth of that circuit, because this is, if we work in power conversion, everyone knows that these circuits are relatively slow, but it's not so common why that is. And one of the reasons is, of course, maybe because we need to do blanking for the reason we just discussed. There was this question on, do we have ringing and so on? Yes, that makes it slow, but there's also inherent already some slow gain bandwidths because the amplifier, if we extract that term here, there's only the amplifier that has a frequency behavior and the cutoff frequency. So the DC gain of that amp plus the cutoff frequency of the amp gives us here the gain bandwidth of the amplifier. And that's multiplied by the ratio of the resistors. And unfortunately, that's smaller than 1, because the MS, that's the sense resistor or sense transistor, it's in a range of 1 kilo ohms, while the output resistor is rather in 100 kilo ohms range. So you have a significant reduction of the gain bandwidth of the amplifier, even though it's just a one loop or just a one pole system, which makes it fast, but this is really degraded and relatively slow. And that's the reason why you find that more for, let's say, low bandwidth current sensing. But it fits a lot of tasks in DC-DC conversion. Now, how to implement this amplifier in reality? There is a very common circuit. So this is again the principle. And in reality, we use this kind of common gate structures here to build this amp, to balance these two voltages. So in the end, at the output stage, we have the now a current. It's the device current flows here and here due to the common gate arrangement, right? To bias everything. So in the input node, it doesn't matter because I bias is in the microamps range. It doesn't matter compared to the main power current, the main load current. But on the output side here, I bias really matters. In fact, our output current is I out, gets I bias subtracted. And that's why I'm adding here these blue compensation paths, which feeds back the I bias from the input so that in the end, our I out is precisely controlled and compensated. That's the second line here. So the input current is equal then, really equal to M times the output current. So we get the proper scaling. What we cannot address is the lower limit of the input current. Since we have a bias current flowing here, which is scaled basically by factor M to the input current needs to be greater than M times the bias current. So that's our lower limit. We cannot sense below that. That's usually not a real limitation in practical designs. So I didn't mention that there's, of course, the typical analog properties of mismatching, which bring errors. Absolute variation of R out comes into the equation in terms of precision. There is usually these circuits are trimmed. So R out may be a binary weighted array. And so we can trim it and even store the trim values in non-volatile memory so that we have a precise current sensing here. With that, I'm watching a little bit the time. Yeah, so we come to the system design topics. And that's just a few slides, which hopefully are interesting as well to look at. Of course, we talk about power circuits. There's a large current. There is also large voltages. We need to have some kind of protection. And that's illustrated here again. We have the circuits of the gate driver. And now the focus is on this protection, right? The power stage and protection. That can be thermal protection. Yeah, we have the power dissipation. We may get some heating that needs to be protected. Then we need to protect against overvoltage of the power transistors. We talked about it. There was this question on ringing, and it's easily, we exceed the max ratings. Overcurrent needs to be protected and detected. We talked about current sensing just a second ago. And then there are these three, usually these three cases come together. It's short to ground, short to battery, and open load. And finally, there's much more, but finally also undervoltage is important, undervoltage lockout, to ensure that we do not start the switching activity if our drive voltage is not at the proper level, because then our transistor would not reach its low RDS on value and our voltage drop simply would be too large. In the end, we would get overheating and our thermal protection may kick in. I don't want to talk about all these blocks just because time is limited. As an example, I would like to talk about thermal protection. And that's usually installed as a secondary protection. If our current limit doesn't work, whatever, the chip heats up, then we detect this failure case by a circuit as shown here. And I like it because it uses the classical Broca loop to generate a signal that's proportional to temperature. We use bipolar transistors we use a single one and then n times that transistor. Could be, for instance, 8 times, because then we can fill a nice array 3 by 3 with these bipolars. And the currents are balanced. They should be identical in both transistors. As there are n transistors in parallel, we have a little bit lower base emitter voltage compared to the other one. And basically the delta VBE is proportional to temperature. So, and by using a resistor, we can convert it to a current, which is then mirrored around as an IPTAT current proportional to absolute temperature. And that, if that ramps up over this resistor here, as shown here in the temperature diagram, the blue line, we may exceed the base emitter junction, or the forward voltage of the base emitter junction here of that guy. Then we turn on the thermal shutdown signal. So that's a well-defined temperature. Of course, the base emitter has a negative and highly nonlinear temperature coefficient. That's something that's a little bit tricky, but it works. And the nice thing about using bipolar transistor is we can use a satellite, more than one transistors in parallel, and place them all over the die. And wherever is our hotspot, that will indicate we need to cool down our chip. That's the basic idea. To increase the precision, we may use some cascode devices to keep the collector voltages identical and feed the base current and so on. There's a little bit detail, but I think you know what I mean. That's an example of the thermal protection. So that brings me to a general system topic, floor planning for power, for DC-DC conversion and top-level design. Of course, we have high voltage, low voltage domains, and usually they are separated by spacings. And that's why we want to have a very clean floor plan and don't want to intermix high voltage blocks, low voltage blocks, and we don't want to intermix analog digital, of course, as in conventional designs. So it's because we want to be area efficient here. Yeah, that's an example, right, for the different domains that we don't want to intermix. And of course, for high currents, we benefit from copper metallization that's available in most technologies that are suitable for power management. Then, yes, we talked about thermal protection. Also, thermal analysis may be quite essential to identify the blocks that cause hotspots on our die. So, and that helps us to place these thermal protections and so on. The next topic is mechanical stress. Usually these dies often can be quite large, and then we all know if we bend it, then we get some stress, and that may cause some shift of precise analog bias levels and so on. For instance, bandgap voltages, if they are not placed in the center, they will be really affected. And I've seen it myself that you easily achieve 10 millivolts, 20 millivolts of shift in bandgap references, for instance. So we don't want to place these blocks at the peripheral of the chip. And of course, it's self-understood. We need to keep the noisy lines and high current supply lines away from sensitive analog signals, as in any other design. So with that, I'm approaching the end of my lecture today. We discussed the DC-DC converter building blocks as a link, or a DC-DC conversion in general, as a link between our system level voltages and the IC level voltages. We want to achieve the optimum efficiency if we do the power conversion. And we talked about building blocks such as transistors, gate drivers, level shifters. Then we went into control loop design, and then we put everything together on system level. So I also would like to thank at the end you for following and also for your questions. And we can also discuss more questions in a second. I also would like to thank the IEEE Solid State Circuit Society to support this distinguished lecturer talk. And as I mentioned to you, I prepared some references here at the end for you to refer to and get back to. At that point, thank you very much.
Okay, thank you. A question?
I suggest that for the question, just raise your hand. You have a button to do that.
Okay, can I start?
Okay, Tovia, start.
Is there any techniques for fault tolerance to increase the reliability of such a converters? Because in some systems, the regulator might be the major cause of failure.
So you were a little bit difficult to understand. So I got, is there any technique to investigate or to find out the reliability on the reliability? But the second part of your question, I unfortunately didn't understand. The acoustics was not loud enough.
For improved reliability, in case that there is, for example, overcurrent or any other problem inside the chip, or any damage or discontinuity or whatever, there is a technique to put two regulators in parallel and combine them in some way without losing efficiency to achieve fault tolerant. So if one regulator fails, the other one will maintain the voltage.
Oh, yes. I think that's common practice to have a redundancy. I know that from monitoring blocks like voltage monitoring. There they like to do this. If you have like two converters in parallel, it's doable, right? Because if one gets out of order, then the other one takes over. That's possible. I personally don't have experience with that. And in terms of reliability testing, of course, all these techniques like we have seen like the thermal shutdown or the thermal circuit, that needs to operate at much higher temperatures compared to the regular operating temperature. So in back-end of line testing of the IC, you usually don't want to go to 200 degrees. That's something that's verified at bench level. Then you do a lot of things to verify reliability. You do like high temperature, operating lifetime, stress tests, and so on. And then the goal is to extract from the room temperature characterization and room temperature back-end of line testing for each chip to expand or to extrapolate that the whole thing works also at high temperature. That's the challenge and to be managed.
I have a question about the loop dynamics.
Sure.
You made the point that when closing the feedback using current rather than voltage, we don't have this second order behavior of the LC, so that simplifies things. Is that commonly done?
Yes, a very good point. That's commonly done. What we basically, I can try to go to that slide. Let me think, it's maybe around slide 20.
Yeah, you went through the whole loop very briefly.
Yes. Yeah, I went to it only briefly with respect to time, right? But just to explain what we do, if we go to current mode control, we basically measure the inductor current. So that can be done either by using this replica sensing that I addressed, or you can simply measure the voltage drop across the inductor. That's also commonly done, right? And now you feed that voltage signal as a ramp signal into your loop. And now instead of applying the sawtooth generator, we apply that ramp signal to the comparator. As you can see, there's a second loop, the inner loop and the outer loop. That makes it complex. But now we can do the calculation. This inner loop, simplifies such that it is really a one-pole system. All these different blocks, they don't matter. It is really like basically a conversion from a current into a voltage domain by the current sensing, and there's no dynamics with it. So it's really that doesn't introduce any additional poles and zeros. And since the L is then disappeared in our block diagram, we simply have to transfer behavior of the voltage loop. And so that's only a one-pole system, or basically, let's say, the control to output, this transfer behavior, this is a one-pole system. And now we can very simply add a compensator circuit to get enough loop gain. That's the point.
So it does not replace the voltage feedback, it complements that system?
Right. The voltage feedback actually remains. We just add a second control loop, which is usually scary, right? A second loop. But it's, in this case, it's really nice to handle because with the loop dynamics, this disappears the inner loop and the outer loop remains. That's the one that really helps us to control in a similar way as it is here.
Thank
in
you.
the voltage mode control. Yeah. If you're interested, I can simply send you 1 or 2 slides which have all the theory in there. So just send me an email. It's really easy. I will be happy to.
Thank you.
Yeah, because it's a very good point. Everyone who is in control loop design, in power control loop design, they all know that from experience, and they all claim it's very simple. And then, but it's very hard to find a analytical derivation why it is a first order system. And that's what I have in 1 or 2 slides, because I had to do it myself and then I prepared it and I just left it out today to not overwhelm the presentation. That's simply the point, right?
Thank you very much.
Sure, you're welcome. Thanks.
SCD guys?
Yeah, this is Claudio. Hello, Bernhard. I have actually 2 questions, two short questions. One is regarding in imagers you require DC-DC converters like charge pumps that are very, very low ripple in the microvolt range. So if you can comment, how well can you control ripple, and what's our good recommendation?
Yeah.
My question is if there is some way to benefit from FinFET technology?
I don't know about if you benefit from that, from FinFET technology or something like that. I feel, of course, that's the limitation of switch mode conversion. This is the point here, right? The output is buffered by a capacitor. The capacitor has an ESR as well, right? This is not just a capacitor. There's also a parasitic resistance, and that always causes a ripple. So whatever you do, even if this capacitor gets really large, you still have some ripple, and nobody wants to have a large capacitor, but that's the way it is. But the common practice to get a low ripple here is to add a linear regulator after the switch mode regulator, which basically sees only a little voltage drop of a few hundred millivolts across, so that it also doesn't degrade the efficiency that much. But this regulator allows to get very low ripple. It basically cancels all the ripple that comes from the remaining switch mode activity here. And then the linear regulator gets really a clean, noiseless output. That's the common practice. However, I know that there are some products that already are able to achieve very low ripple and very low noise without using linear regulators. But to be honest, I'm not so familiar with all these techniques.
Okay. So your best solution would be to some low dropout, like an LDO regulator. And
yeah, the LDO. So of course, if the input voltage is quite large, you would first use this kind of buck regulator, switch mode regulator, to bring the voltage down by a big portion, and then leave only a little bit of voltage that the linear regulator can handle. And of course, we know the voltage drop across the linear regulator is losses, and we want to get these losses to a minimum. So typically you have a voltage drop across the linear regulator of a few hundred millivolts, like 300, 400 millivolts, right?
Okay.
Yeah.
Okay.
Sure.
Okay, it gives me, I have two small questions. The first thing is in your experience when you decide the DC-DC converter, because we have to care about some application like the battery power applications. So in those scenarios, we really care about the idle stage. That means we care about the quiescent current of the controller. So what is the techniques to reduce as much as possible in your experience?
Yeah, there are some controllers on the market that are really ultra low power. They usually try to get the power down by reducing the switching activity here. And what they do is they go from pulse width modulation into pulse frequency modulation, or sometimes called burst mode, which allows to turn off most of the components here. What they leave in is a comparator that observes the output voltage. And once the voltage drops below a certain tolerance level, then it activates the whole circuit, sends a few pulses of energy pulses into the system here, and then goes to sleep again. So and that allows to achieve very low power consumption. So it can be the overall power consumption in low power mode can be in the 100 nanoamps range, few hundred nanoamps range. That's something some ultra low power products can show that already.
Yes. And my second question is, in your experience, what is about the EMI of the switching converter? Because I think that for the buck converter, for example, the input current is the discontinuous one. So how can we deal with that? Do we need to add the, external RC filter, or just sometimes we just only we have to add only the single input capacitor?
Yeah, of course, it's not shown here, but we always need to have a capacitor at the input and as close as possible to the power stage, because we talked about, there was this question on the parasitics. There is, the longer the distance, the more L we add here. And we see, of course, current spikes within here. So that causes little voltage spikes, and that's visible in the EMC spectrum. In general, that's these switch mode circuits here, they cause some EMC noise. Some comes from the parasitic inductance due to the dIdt transitions. The other component comes from simply from the switch mode pattern, right? We get a rectangle here, and that's sending broadband noise. So we basically see both noise contributions, a broadband noise coming from this, I would say, rectangle trapezoid shape, and the other one is a small band, smaller band, which is current ringing. That usually occurs as a peak in your spectrum in the 50 to 100 megahertz, few hundred megahertz range. So, and in order to address that, there's various ways. You need to have, you mentioned it, of course, I think there's no way to get away without an EMI filter at the input, unfortunately.
Yes.
And then there is some additional things we can help with on the design side. The slopes here of these drivers, they could be adaptive. That means if we are in a sensitive operating mode or an operating mode at maybe at low power, we can afford maybe some more switching noise. We would simply decrease the driving strengths of these drivers. We have seen these cascaded drivers. You could change the driving strengths here simply of these inverters. So that would help. Then we have less lower EMC contributions or EMI contributions. What else can we do? Yes, there is some concepts that are called resonant conversion. So they do not apply hard switching, rectangular control. They let this LC ring so that we have a resonant behavior. And so instead of rectangular noise we have, or contributions here, we have sinusoidal, mainly sinusoidal waveforms. And that also really, really helps in the EMC spectrum.
Yes.
Yeah, it doesn't solve it. I mean, there's always EMC. That's for sure.
Yeah, many thanks.
Yeah. So
yes.
and I know that's something also we have done some research on resonant conversion, how that helps to get our EMC noise down. But to be honest, that's something I still want to follow up. I think there's more to do on the research side. So that's something I feel will more and more come up.
Yes.
Low noise DC-DC converters, low EMC noise DC-DC converters is still a topic that's not fully solved.
Yeah, frankly speaking, I just want to talk a little bit about this because usually recently I see some new topology. They mention about the hybrid converter. So they move the inductor from the output to the input. So in that case, they transfer the input and the output current to become the continuous one. And hopefully we don't need any external LC filter anymore to reduce cost.
Yeah, that's one of the benefits we had at I think at the ISSEC, not this year, the year before, we had several papers on placing the L to the inputs. And one of the benefits was really to get your EMI better under control. And I think there was even in one of the follow-up journals, there was even EMC measurements or EMI measurements presented.
Yeah. I remember the papers.
Yeah. Of course, that's all the papers is one thing, and how it goes into products and how it really proves to be robust enough. That's always different. I know that.
Yeah, thanks.
Yeah, but thanks for bringing that question up as really something I feel there could be more done. Yeah.
Any other questions? If not, then thank you again.
Yeah.
It was.
And I'm sorry, but the last question is: could we, see the presentation files after the meeting?
Yes, that's what I was about to say now at the end. I will provide these slides. So Masha and Shahar will have these slides. In fact, I sent it already to Masha, so they can be distributed. That's fully all right.
Yes.
Yeah.
Thanks a lot.
Yeah. And there's also my contact info, or you can Google me anyway. If you have any questions, I will be happy to answer them afterwards, or even later. If in 3 months you have some questions, don't hesitate. I will be excited to answer you.
Yeah. Thank you, Professor.
Yeah, thank you for your questions. And thanks everyone for joining. I really enjoyed it. And I also enjoyed that we have the discussions while I was talking and afterwards. So thanks a lot for that.
Yeah,
so,
thank you. Yeah.
Thank you very much.
Thank you. Thank you so much.
Thank you. Bye-bye. Take care, everyone.
Thank you very much.
Bye-bye.
Bye-bye.
Bye-bye.